I was thrown out, and I think somebody else among you, it's very likely it will go to him or her. So the rule is that the moment you have the transcript coming to you, the intimation, so you should transfer ownership to me. Okay, and also there will be another mail for the meeting details. Okay, so that also you should transfer to me. So that is basically giving the, yeah. So it is started recording. So most likely this will go into somebody else's account because I had logged in and then I was thrown out.
No, sir.
So
Actually, this one will go to your account because it was written that and Banerjee started recording.
okay, was it written? Okay, I
Yes.
don't know. Hopefully it will. So anyway, I've told this many times, but still people, that if you don't transfer ownership to me, I cannot put it to the class drive. So whatever happens, you have to do that. Okay. Acha, so as we had, so this is a very interesting, discussion we had last class. Today we will continue from there. In fact, today we will actually discuss the philosophy of the whole thing. I mean, in the sense that what we discussed last class was just to tell you that how the construction of Fresnel in order to understand how when you have a spherical wave front and the Huygens sort of assumption that or not assumption really, Huygens theory that all points of a wavefront, spherical wavefront, would also give rise to secondary wavelets. That was used by Fresnel, and he sort of found out means in terms of. Oh, was I thrown out again?
Yes, sir.
I was thrown out. Anyway, I seem to be back. But yeah, as I was saying, I will just use this construction once more because I
So
think
you're
this is
not
very.
presenting.
Yeah. Oh shucks. Oh, sorry. Today is going to be a bad day probably. Yeah. So we're back. Anyway, so the important thing is this was the construction, right? This was what we had sort of come up with, the Huygens Fresnel theory of diffraction. And what we found out basically was that this was the point source at P0. You want to find out the effect of this point source at P. And so this is like a spherical wavefront, which is just about, the radius is R0 from this point P0. And each point of the spherical wavefront gives rise to secondary wavelets. And they are sort of superposed to finally form the field at this point. And what we the construction of Fresnel in order to in order to sum up all these wavefronts was basically to create things called these zone plates, where you actually have these different sort of circles which intersect on along arcs on this wavefront, and each of these are called zones, and then you find out basically the contribution of each zone on this point, and then you add up the contribution and you find out the total field. So what we found out as the total field was something like the field at UP was finally given by so when we assume that this k so the expression for the total field was something like before we summed up everything was something like 2 I lambda minus 1 to the power j plus 1 kj. This is the inclination factor which whose value we found, but essentially this was the contribution of our each zone, some kind of a this is a problem. You come too close, you can't write. Write again. So essentially what you have is u of p is given by 2 I lambda minus 1 to the power j plus 1 kj a e to the power I k r0 plus b divided by r0 plus b, where this is of course r0 and this is b, and this is the total distance between these two. And we know that the first zone has maximum effect, and as you go out, the zone's effects start reducing. And what we finally saw is that when you actually summed up, oh sorry, I think this is not correct. This is not correct. I should just write down the summation. Sorry. So this, and then there is of course the summation. Yeah, this whole thing should be summation. Yeah, what am I writing? So basically, I think it's best if I just write this as 2 I lambda this, and then you basically had j equal to 1 to n minus 1 to the power j plus 1 kj. This is what we had. And then we summed up this whole series by Schuster's method and found out that it is essentially equal to k1 by 2, using these arguments of, that you basically had the arithmetic mean of, the any kj can be either smaller than the sum of the arithmetic mean of the number just before it and after it, or it can be greater. So we did the greater case, and I think if you look at the lesser case also, when it's like the any kj is smaller than the arithmetic mean of the numbers preceding and succeeding it, then again you will get a similar kind of result. What is interesting now, so we just got this, and now the effects of this is very important to comprehend. So what you actually find is that if I just, so one thing here, so remember that we got the summation to be this, and the total field we basically got to be something like yeah, so this came up to be I lambda, this was summed up to be some I lambda k1 ae to the power I k r0 plus b r0 plus b. And then we said that for this whole thing to be a spherical wave, k1 had to be equal to minus I by lambda, which means that this up was essentially equal to yeah, so just ae, yeah, so this had to be just ae I k r0 plus b divided by r0 plus b. What you must now understand is that, so I had told you that essentially diffraction came when you put obstacles. So what do these obstacles mean? So you can either, so see, the obstacles might be put here, or interestingly, I think the obstacles might actually be put on this wavefront itself. In the sense, I might actually just, so that is one of the main also, justifications or the advantages of using these zone plates. So what clearly you see, suppose I have some kind of an aperture where I only have this first zone open and everything else closed. So then what will be this u1 of p due to the first zone from here? Very clearly, that is just going to be 2 times k is k1, just k1, right? Minus 1 whole square, so k1 we know is minus I by lambda. So it's basically going to be 2 aeik r0 plus b r0 plus b. So this is actually, if you turn on everything open, if you include the effect of everything, that is actually smaller than if you have only one open. Do you get this? This is fantastic, right? So this implies that the intensity of I1P is 4 times that of the total intensity, right? Because this is twice A and this is just A, right? So now just think of this. Essentially, this is all what. So what is the take? Why do you think this is happening? What is the physics? What does this mean physically? What does this mean? That if I just have one zone open, the amount of light that I get here is actually more than if I have everything included. So what is this telling you? What is this telling you?
So this means that light has some kind of a wave nature, because if it was just simply
Exactly.
particles, the intensity would simply
Exactly.
add up.
Exactly. Exactly. So this kind of, and so this is only possible when some of the other zones are going to kill off the amplitude at this point. So this is a perfect example, or you can say the confirmatory test of superposition, or rather I should say of the wave nature of light, of the wave nature of light, because this illustrates superposition of waves. Only and only then can you actually have the intensity due to the first zone. When if you only have, so basically what I'm saying is, I should just write this down: block all other zones except zone 1. So what you get is this, U1P is this, and that means the intensity is 4 times the total intensity. So this is fantastic. And in fact, what happens? So let me ask you this, guys. What happens if I do the other thing? In the sense, suppose I just block the first zone and allow everything else to go. What will happen? Suppose we block zone 1 and allow all other zones. What happens? What will happen? What will happen? Yeah, guys? Very simple, right? Kya? What will happen? So basically, this is block, matlab kya hoga?
We'll get what is it? The first zone.
Hi, Joe, Rohan, I'm saying I block this. Okay?
Oh, okay.
So I'm blocking. This part is blocked. Blocked. So basically, I'm putting a stop. So you have light like that. Suppose I'm whatever, I'm putting a stop. Block. What does that mean?
So you'll get the same intensity as
Is
one.
is this clear to everybody? What Anirudh said is absolutely right, but is this clear? Why you'll get the same intensity? This is
So
fantastic.
because the
This
net
okay.
goes
Let me
by
just
k1
write
by
down.
2,
Yes, exactly. So let me
and if you
write
subtract
down.
k1 from that, you'll get minus k1
People,
by 2.
Rohan, you guys are not thinking, yeah. I hope all you understand.
Yeah, yeah, I got it.
Very clear, right? It is absolutely clear, no? So
I
this
thought
is
you
the
were
thing.
blocking everything else except one.
No, वो तो पहले ये था. ये इसमें I bought all zones except zone 1.
Ah, okay.
That was this. Then you get 4 times. I am now doing the other thing, right? So यहाँ पे क्या होगा? So if we block Z1, then K1 is 0. But then this will just be then minus K2 plus K3, etc., etc. And in the same logic, this will be just minus K2 by 2. Exactly what we had here. The same thing will hold, right? So then the total sum will be exactly the same, because you know, so total sum, this is the total sum, and we know that K2 is almost equal to K1. So this directly tells you that intensity at P will be the same. And this, guys, is exactly what diffraction is. What did you study in school? You studied in school, you would define diffraction as bending of light around obstacles. This is exactly that. This is exactly that. You basically, what is happening? Can you realize what beautiful this is? We are blocking this for completely. That is, nothing is happening to the light. It is same intensity is coming here. So it is as if light is just going around this. But when will this happen? When will just light grow around this? When is this thing happening?
Wave.
Yeah, wait,
When
no,
light
but
is a wave. Your audio is gone again.
also very other crucial thing, Anirudh. Essentially the obstacle, these massive, so then there is this another very important
Sir,
thing that comes.
we couldn't hear your last minute.
Last minute, oh shucks, Anirudh answered.
Yeah, yeah.
Arey
So,
yaar.
No. After that, you said something important and we missed that.
Oh, no, no, no. What I was trying to say, oh God, again, this connection. No, so basically, what I'm trying to say is that if you are actually, see, this obstacle, this is just zone one, right? So essentially, if I have, see, remember the difference between these zones is only of the order of lambda. So that is what is crucial. So basically, the blocking thing, the circles, the differences are only of the order of lambda. So that is the reason. So, and remember, this thing, this diameter is also extremely small. That is not so. Then here there is another very crucial concept. So let the diameter of a zone be, say, some A. Okay. So then, so basically, what I'm saying is that this kind of, so this, so let me say, yeah, this is my thing, right? So if I just think of this diameter of this part here, if that is A, like this part is A, from here to here, this part, right? Then let me draw this properly. So essentially, if this is like that, and I'm breaking this, and I'm saying this part is A, right? So what happens then? This thing is A. So then the diameter of this zone. I should not say diameter of the zone. Maybe I should say the diameter of the obstacle. Let us see what is better to say. Uh, yeah, so maybe we should just say there's an opening. Yeah, that's better. So we just say that there's an opening of radius A. So I'm not, see, the diameter will actually come from this, na? So this, let me just say that there is let there be an opening. Let there be an opening on a zone, or oh yeah, yeah, opening on a zone of size A, right? So that happens. Basically, then what you will get is, if you just have an opening of this size A, then uh, then the diameter of the zone, right? Then the diameter is actually given by nothing but A squared plus B square, right? This is nothing but A squared plus this one is A squared plus B square. So then this is also equal to, remember, if that is like the nth zone, then that is from what we got from last time. uh, uh, yeah, so yeah, so that is basically also equal to B plus n lambda by 2, right? Because that is what we had seen when you keep on increasing, when you go to the nth zone. of lambda by c. Say I say this is nth zone. So that is like b plus n lambda by 2, right? This is b plus n lambda by 2 because that is what we had. So now if I assume that your if I assume if b is much greater than a, then this a square plus b square to the power half is nothing but b 1 plus a square by 2b square, which is equal to 1 plus b plus a square by 2b. Remember, this is fine, right? Because this is was the diameter of the zone that we had defined, right? So that means what? This b plus a square by 2b is equal to b plus n lambda by 2, which tells you what? That this is cancelling. So then a square, so you will basically get this you'll essentially get a square by b lambda equal to n, right? And what was this? A square by lambda b. Where did you see this before? A square by lambda b equal to n. Where did we encounter this before? Yeah. Array.
Fringes, I think.
No, this was the Fresnel. Yes, exactly. The Fresnel number, right?
Yes.
In my resonator. So what did we say? This was essentially the size. So in order to ensure that the Gaussian beam is completely entrapped inside the cavity, it is essential that the the size of the mirror has to be greater than this thing, right? So this is where you sort of came about. You had to ensure that this a square pi was much greater than b lambda, right? This n has to be much greater than 1. So here what it means, so this is basically telling you in this case number of zones for an opening a along the wavefront. Do you understand? So the diffraction essentially means that suppose I have everything blocked. So let us see like this. Suppose you have an aperture like that, right? And then you have this wavefront, spherical wavefront coming like this, right? So essentially this is my A, and this is the size of this essentially tells you how many Fresnel zones you need to consider from your screen that is at a distance, whatever this is, B from here, right? And that exactly tells you that there is superposition happening. The interference between these wavelets is giving you diffraction. Isn't this beautiful? So this is really what diffraction is, right? So you basically that is, and this was Fresnel's brilliance. So the obstacle essentially comes in as how much of the wavefront is blocked, as a result of which how many zones you need to consider in order to find the field at the point P, which is on the screen, right? And this is where you remember this Fresnel number gives you the number of zones. So it is slightly different in for a cavity. Of course, you need to ensure that this is very large, so that you essentially don't get any. So actually, if you see this, if this is extremely large, then is very large, you actually get a sort of a fixed intensity. You get you yeah, so you can see that depending on how big you make this obstacle, you can actually get, so suppose so can you tell me, okay, let me ask you this, how can you get darkness here? How can I get complete darkness on the screen? Oh shucks, what I'm trying to say is, how can I get complete darkness at P. What do I need to do? Yeah, how can I get complete darkness at P? Got the question, right? I want complete darkness. How will I get it?
Either you block all the zones or block the
Then, so
ones,
that is trivial.
or
That
the
is
blocks
trivial.
such that the ones which are remaining like interfere
No,
and
no.
create
Give
darkness.
me a actual answer. No, what should be the size? How many zones should I allow if I want to get zero?
Sir, I think you have to block like a ring. There should be the
अरे
central and the part outside the ring. I don't know
अरे तुम
exactly.
इधर से प्रिया नो इधर से बोलो ना. Just from here you say where is that thing that I here इधर से बोलो. How many zones should you block? How many zones should you allow rather? From this. From this, how many zones should you allow to get complete darkness? Almost complete darkness. Huh? See, you guys are still not completely understanding this.
Greater than the Fresnel number.
No, man. Oh, what is the series? The series is K1 minus K2 plus K3 minus K4, right?
That
So
will
if you
go
allow two zones, no, if you allow two zones, you get K1 minus K2. And K1 is almost equal to K2. You understand? They completely cancel out. Right? So if you allow an even number of zones, very clearly you can actually almost get nothing here. If you allow an odd number of zones, of course, you will see some effects. So the basic interference comes because you are actually getting a change in the sign in this total series. It is minus 1 to the power j plus, right? So k1 minus k2 plus k3 minus k4 like that. So if you just block every other Fresnel zone except the first two, you will get darkness. Is this clear?
Sir, how would we do that?
Huh?
Like
So
how
just
explain
इसका
how
size
would we
का,
know that
hey,
these
come on.
two are
So
the
this is
first
coming from the series, na?
that is
This is
fine. I'm
from each
asking
zone. हाँ तो
experimentally how do you do
so
that? Is that you
just you
just see
take
the darkness and then you
no
say
no no
कि
no
yeah
no
this
no
is
no no he takes very simple, right? तो एक ये लो, so you have this thing, हाँ इसको पूरा block कर दे with an aperture and you have a small opening outside. इसको बढ़ाते जाओ, you have an aperture, right? These ring apertures can be opened. So have an have a sorry have not an have a controllable aperture. Increase the size.
Sir, then the last and the second last also have K1 approximately equal to Kn minus 1.
Yeah, but then no, but how much do you have to change, right? How much does K1 and K2 differ? What is the change you have to do to the aperture size? How much? Huh? How much do you need to change the aperture size? Arey, each zone differs by how much from each other?
So B changes as lambda by 2.
Yeah, yeah. So if you could get the possibility of changing these, so essentially, how do I get allow an even number of zones each okay, let me just start this even number of zones, right? And but then of course the caveat is, so therefore basically an experiment with a with an aperture whose size is controllable to lambda by 2 is needed, which is tough, I mean, having a aperture which is like, so therefore so you can say, tell me, for example, in the lab we almost will never get this right, because whatever micrometer scales you have seen in our lab, that is mostly like a few 10 microns sort of resolution, right? So if you change by one, you get thousands of zones coming, right? So you will never get darkness that way. But suppose you were you were able to change the aperture size to the level of 300 nanometers. If the wavelength was 600, then actually by changing 300 nanometers you can go from light to darkness, right? So this is absolutely actually great actually. So if you yeah, so in principle you should be just able to in by this theory, provided of course you have apertures so small. That is extremely crucial. So the first aperture itself has to be so small, you understand? It should be very very small, and then you have to keep on changing by lambda by 2, right? So then so this is there is a bit of a problem in the sense that the first aperture itself cannot be very big. So if you could actually ensure that you had an extremely small first aperture, okay, so if it's completely shut, and yeah, so basically this is the dimension, right? So you want this to be only one zone, then you can just get from here. Yeah, you can get from here how much. So yeah, you can very well see that the smaller the b, right, then you essentially can no the sorry, the larger the b, the larger you can have this zone, right, for a fixed lambda, right? So but then this still gives you a very strong constraint. I mean, you need to really get this extremely small and look at very far if you really need to go by this, if you can actually go by this. But mostly it doesn't happen. Mostly we just see diffraction through a circular aperture because the obstacle that we have typically is much larger. So then many zones are allowed. Then of course we have a different thing. So that is what we are going to look at: Fresnel and Fraunhofer diffraction. But this is very beautiful. Do you really, everybody appreciates this, what I said? Do you really understand? Yeah? Any issues, tell me.
So this can be demonstrable using a longer wavelength, right?
Yes, correct, absolutely right. But then उसका झमेला है, अनिरुद्ध, तेरे को कुछ, you will not see anything, right? वो बहुत प्रॉब्लम है because वो रेडियो वेव से करेगा तो कुछ विजुअलाइज तो वेरी टफ, वो माइक्रोफोन
हाँ,
माइक्रोफोन से
विजुअलाइज
करना
नहीं,
होगा,
बट डिटेक्टर तो है ना.
माइक्रोफोन से करना, हाँ हाँ, माइक्रोफोन से you can do absolutely. You can try. I mean, microphone, say if you put a receiver and all, in principle this should work. Okay, so basically this is the whole thing. Now let us do some quick understanding of Fresnel Fraunhofer. Uska matlab kya hai? I mean, that is much simpler than what we have done till now. That is mostly definitions. So let me just write down Fresnel and Fraunhofer diffraction. And what we are trying to do here is sorry, 1 minute, let me take the drawing here. Ah, okay. So the basic thing is, as I said that time, this is what we were trying to do that time. So you have an input field at this plane, which is epsilon x, y, 0 along the z-axis, and you want to find the the electric field at some epsilon x, y, z, right? So we now know from what we did this whole exercise now that if I want to write down this field here, it is epsilon x, y, z, that is nothing but minus I by lambda e to the I k r, ah, sorry, something will go, sorry, e to the I k r by r
Whatever we did
epsilon.
in the previous section, that is only true
Sorry,
for
what?
the spherical wavelength. Oh, sorry.
Yeah,
So
yeah. No,
the,
but that is what we're assuming, right? we are assuming that if we have a point source here again, and this is the same problem that I visited, but I basically see this is what we learned from that, right? This is exactly what we learned. This is exactly what we learned. We derived this, why this is going to happen. Hai, this is exactly what we learned. That if you have a point here, this is my XYZ plane, basically XZ plane rather, XZ plane, and I have the field at some point P which I want to measure. This is exactly what we learned, right? And so, yeah,
That would
maybe I
be
should
for
just
the
say this as
spherical
Z time.
wavefronts.
No, but this is what happens, right? If there's a point source, you will have spherical wavefronts.
Yes, but if you
If
have
there is a point source, it will have spherical wavefront. And so, but that is the whole theory of diffraction, right? You are essentially thinking of point sources, and you find out the final field at that kind of at some different XYZ compared to where you started from. That is exactly what you do, right? So this is, and your R is nothing but x minus x dash whole square plus y minus y dash whole square plus z square to the power of half. So Hitesh, you if you're trying to say plane waves when this kya hoga, finally see at the moment we are trying to write down what Fresnel and Fraunhofer diffraction are. Okay, this is exactly what we're trying to do. And the so you can so this is exactly what we learned. Key, if you have this kind of a field here, some point source here, which is giving this kind of a field amplitude, which has an amplitude of this, then after some z distance, this will become here, and you can see that delta A has to be, this is of course a small area, this is a small area around epsilon x dash y dash 0, and dimensionally, in order to for this to match, this delta A also has to be there because you have lambda and r below, right? So that is also necessary. So now you can understand that so basically I can just r this r I can substitute, right? So then this basically becomes your delta E x y z becomes minus I by lambda e to the I k z. Acha. So iska, you remember for spherical waves we had done that, shown that this is very, you can take this z common, and फिर इसको तुम provided that this x dash and y dash, I mean sorry, this x and y are not too much far off the axis, then I can just take that z out, do a Fourier, I mean sorry, do a Taylor expansion and drop off. That is the important thing. The drop off is what basically Fresnel and Fraunhofer are. Okay, so that is the whole point. Anyway, let me just write down e to the I k x minus x dash whole square plus y minus y dash whole square uh, by 2z. This will be half. Half epsilon x dash y dash 0 delta A. Okay. So now this kr, kr that I had, let me just explicitly write that. That is nothing but your k into x minus x dash whole square plus y minus y dash whole square plus z minus z dash. Oh, sorry. Z square plus just z squared half, which means it is kz 1 plus x minus x dash whole square. Oh, actually, ये half नहीं रहेगा. This is not okay. Let us continue. Yeah, half actually रहेगा भी. Anyway, x minus x dash whole square plus y minus y dash whole square by z square to the power half. Okay, so this can be written as kz if I do assuming that assuming z much, acha, this z is, yeah, so is still greater than this part, then numerator, basically we write this as k by 2z x minus x dash square plus y minus y dash square minus this will basically be, yeah, k by 8z cube, right? Second term, ये half रहेगा, yeah, that is z square, yeah, half 8 ही होगा ना, this whole thing square. Okay, so basically what Fresnel, the Fresnel limit one can say is, so for Fresnel diffraction we consider the first two terms. Okay, so basically the Fresnel limit is when z cube is much greater than pi by 4 lambda x minus x dash whole square plus y minus y dash whole square whole square. Is this clear? So a इसको just 2 pi by lambda करके I am writing this. So this is what we essentially define as the Fresnel limit. So this is what it's all about. Okay, this near field, far field, this is that, and your front limit is z square plus y square. Okay, so yeah, so how we, this is, so essentially so guys, are you there with me? You there, right?
Yes,
Hello,
sir. We are there.
you're there, na? Okay, so if I just write, so in terms of Fresnel, what we say is so for Fresnel we basically have your epsilon x y
Sir,
z
can you explain the last
as,
two steps again? Your voice got cut
yeah,
off
so
actually.
basically, oh you go, oh shucks, so basically what I'm doing is I'm expanding this. Okay,
Yeah, that
so
is fine.
Fraunhofer Fresnel में you keep first two terms, Fraunhofer में only this. You don't, when basically even इसमें you essentially it is, so Fraunhofer basically what we keep is, I'll just elaborate this a little more. Let me just write this thing down. Fresnel is very clear when in this expansion, Taylor expansion here, we keep up to the second term. Okay, so yeah, so essentially what you have is minus IE IKZ by lambda z, because remember the integration is on x and y. So epsilon e, rather e or epsilon, whatever you take, 0 yeah, check this once I'm doing correctly. Yeah, so if I just take the Fresnel thing, then you essentially keep up to the uh, yeah, Anyway, yeah. So basically, what we have is, you just write down that this is epsilon. Yeah. So e to the I k x minus x dash whole square plus y minus y dash whole square by 2z dx dy dx. Yeah, this is integral over dx dashed dy dashed. Okay, this is x dash. Yeah, so this is, so for the Fresnel case, so the total, I should not write Fresnel actually. So basically this for the so this is my whole field. Okay, so here when I do the Fresnel part, so remember this is, oh, the integration over is over xy, so I can take that z part out. So essentially when I do the Fresnel part, when I do the Fresnel limit, then in this total expansion I just keep up to the second term, and let me just elaborate that. So if I just take this if I just take, consider this e to the that I k, x minus x dash whole square plus y minus y dash whole square, this thing by 2z. If I write it down, that is basically e to the I x square plus y square divide by 2z e to the I x dash square plus y dash square divided by 2z, and e to the minus I k minus I k x x dashed plus y y dashed by z. This is fine, right? This is just this thing I'm expanding. Okay, so now for the so you can see, remember what I'm doing is, I this is z is okay, so I'm integrating over x and y basically on this, right? So I'm just integrating out the small area element, that I'm actually integrating. So it's this thing is over x and y clearly. So then clearly what you have is this one is independent of x dashed and y dash. This can come out of the integral. So for Fraunhofer, in the Fraunhofer limit, so in Fresnel you need to sort of consider all this, but in the Fraunhofer limit, what you have is your z is much greater than k of x dash square plus y dash square, right? So this term basically goes for Fraunhofer far field limit. Okay, so essentially what I'm saying, what this means is that the measurement distance is so long that you don't really care about the spread of the source. Okay, I mean, in the sense that plot spread, I should say that, this axial, the transverse distance is trivial compared to the distance where I'm actually measuring. So that straight means that my basically what I'm saying is, for points all points x dashed y dashed on the source, so we basically have some kind of a what should I say, so the axial distance is much is much larger. Okay, so then what you get, so basically what you get is that, which means that this eik x dash square plus y dash square by 2z is almost equal to 1. So then what you just get as the field is just this minus I e kz by lambda z e to the I k x square plus y square by 2z integral double integral of y dash 0 e to the minus I k xx dashed plus y dashed by z dx dashed dy dashed, right? So what do you think this looks like, this integral? What do you think this looks like when I write something like this? What is this absolutely, looking like?
Fourier transform.
Exactly. So this is nothing but the 2D Fourier transform of the source. That is what your Fraunhofer diffraction basically is. Okay. So you just take, so when you really measure at points that are far off from the source, what you do essentially is nothing but a Fourier transform of the source. So that is what it is all about. So we will just do that example of a circular aperture. This is because, I mean, you can do it yourself, but I will still, maybe we'll
So
just
I have
need
a
to.
question. I couldn't
Huh,
get one thing. Can you
what,
go
Guru?
back to the previous one?
Hmm. Wait. Yeah.
Uh, yeah, so here this e to the power I k x minus x prime square
Hmm.
plus y minus y prime square. Here,
Hmm.
how did you write the right hand side?
This one. Expand
Yes.
करो यार. X square
So
plus y square.
you'll get
X dash
2x
square
x
का
prime.
तुम्हारा क्रॉस टर्म, इसको
Yes,
जस्ट
that
एक्सपेंड
where
किया.
did that cross term go?
ये x dash, अरे
No, on the right hand side.
हाँ तो ये वाला.
Oh, okay. So that is there. Okay. Oh, I
हाँ,
couldn't.
this is just that thing ना. अरे x को होल स्क्वायर करोगे तो वही आएगा ना.
Oh,
x
yeah, I
x
couldn't find that
x
term. Okay.
x x right. Y. It is not x into y, no. It is just x y
No, no,
x
fine.
is
No, sir, that is fine. I
clear, right?
couldn't see the last one.
हाँ
Yeah. Fine.
हाँ, this is fine, right? So this
Yes, sir.
is the only thing that remains, no? So very clear. Good. Yeah. So the final thing is diffraction by a circular aperture. We are just going to do this one case, very simple. You can just do it yourself. So suppose there is a circular aperture, some d that is equal to 2a, and you have this monochromatic wave, plane wave. I mean, see, this whole treatment, remember, I can basically just put whatever field I am having. I just essentially, you know, I whatever I have, I just, so what you understand, what the treatment told you last in the last thing is that the Fraunhofer diffraction is nothing but the Fourier transform of the source. So whatever you take, it is basically just going to be that. Okay. Incident, and we say that it is some, epsilon x dashed y dash say 0, that is equal to epsilon 0 e0, and that is the same everywhere on the aperture. Okay. So and we also say that this epsilon, this is also important, 0 is 0 on the screen. That is important. Okay. And that is basically, we are saying that uh, yeah, so it is like, this at least there is no secondary wavelet that is reaching. It is like a perfectly, absorbing, for the incident field, it is like the screen is perfectly absorbing or something like that. Okay, so then what you for the field at the screen, that is just given by nothing but this, your just the field epsilon. Say if I say that is like x y z, that is nothing but Fourier transform of epsilon x dashed y dash 0 e to the minus I k x x dashed plus y y dashed by z dx dash dy dashed. And so this is constant, so I take epsilon 0 a to the minus I k x x dash plus y y dashed by z dx dashed dy dashed. And now because it's a circular aperture, we take circular, polar coordinates. Circular, I just not circular, sorry, just polar coordinates. We take polar coordinates, that is x is r cos theta, y is r sin theta, and x dashed is r dashed cos theta dashed, and y dashed is r dashed sin theta dashed. So your dx dash dy dashed is r dr dash d theta dashed. This is very, very standard, right? So then basically what we get here is that this we'll consider this e to the minus I k x x dashed plus y y dashed by z dx dashed dy dashed essentially becomes 0 to r, 0 to a, sorry, that is the aperture size, r dashed dr dashed, and 0 to 2 pi theta e to the minus I k. And ये तुम्हारा अगर this one if you do this actually if you just do your x x y y, oh, it is very clear. So x x x dashed y dashed क्या होगा? Can you tell me? So x x बोलो, can somebody tell me कि x x dash plus y dash simply क्या होगा?
R dash cos of theta minus theta dash, something like that.
Exactly, cos of theta minus theta dashed by z d theta dashed. Yeah. Okay. So this basically is nothing but, so this we can essentially write down as a Bessel thing. So this is nothing but this whole thing is 2 pi 0 to a j 0 k r dashed by z r dashed dr dashed. And yeah, again this is, if you look at standard integrals, this is this whole thing, ये whole thing is just a square by 2 2j1 kar by z, integrate out r dashed, divide by k a r by z, the standard integral. Okay, so then your इसको थोड़ा शायद छोटा करना होगा. So basically what you have, your e of rz or epsilon rz is minus I e to the I k z e to the I k r square by 2z pi a square by lambda z 2 j1 k a r by z by k a r by z. And very clearly this is independent of theta. This is circular symmetry. It's the problem has circular symmetry, so theta is gone. Okay, so then done. So if you now say isko k ko tum agar we have some k f a सब है, इसको 2 pi by lambda अगर ठीक से लिख दो, let me go to a new screen. Diffraction by circular aperture continued. So if you put k equal to 2 pi by lambda, you basically get your I as some I0 in incident intensity pi. ये सब थोड़ा देख लो. This thing whole square 2j1. This is basically, what did we have there? KR. Okay. So 2 pi AR, 2 pi AR by lambda Z divided by I whole square. This whole thing is actually whole thing. I'll write whole square. Whole thing whole square. 2 pi AR by lambda Z. This whole thing is square. Whole square. Okay. So basically, if you just plot this, in the intensity will, it's basically ऐसा type का दिखता है, ऐसा type का, is lower like this, ऐसा type का, ऐसा. So this is some pi, 2 pi is somewhere here or something, ऐसा type का, minus pi, oh, sorry. Choose minus pi, whatever, all that. ठीक है, it is so at 1 it is this thing, and the intensity, this is the E of, this is the E, and this is plotting 2j1 x by x, this axis. Okay, this axis is your theta, and this is epsilon r theta, and the field, of course, sorry, the intensity is clearly ऐसा type का, just you square this and this that. Okay, so then you can also see that the max intensity is just ये पूरा 1 हो जाएगा. It is this I of say 0z, if I say, that is pi a square by lambda z whole square I0, and so I can just write this I of rz as I of 0z 2j1 2 pi ar by lambda z by 2 pi ar by lambda z whole square. So either say, how do you think we can find out that this thing, you know that so अच्छा, by the way, this is, इसका नाम क्या है पता है? इसका नाम, this is famous, this name of this distribution, this is called the Airy pattern. So basically you get these rings, ऐसे type का rings when you focus. So this is the same thing that happens when you actually focus by a lens. Exactly ऐसा ही type का आता है at the focal plane. Okay, and how will you, for example, get the diameter of the first ring? Huh? How will you get the diameter? Basically, ये diameter कैसे मिलेगा?
We find out where it becomes 0.
0, right? So I1 at x is 0 at x equal to 1.22 pi. This is 1.22 pi, right? So that means this 2 pi AR0 by lambda z is 1.22 pi, and you get to the famous relation of R0 lambda z by this 2a, if I say, generally this is called as d. So r0 is 1.22 lambda z by d. This is exactly, so how is this? So basically तुम्हारा अगर ऐसा है, this is your screen, तुम्हारा ऐसा plane wave आ रहा है, and ऐसा type का screen में आ रहा है, you have pattern like this. So if you just say that this is like, so this is like a theta, then this is basically what is r0. Okay, so this is what we also call the Rayleigh criterion or resolution. Remember exactly. So now if I say, this is quite clear that r0 by z is 1.22 lambda by d, which is actually this theta 0 or whatever you say, theta, it's a theta 0, this theta. So this 1.22 lambda by d, ये कहाँ पे और देखा था? Something very close to this. Where did we see?
Resolving power of telescope.
No, in our thing that we studied just before this, where did we see this? This kind of lambda ऐसा type का this thing, lambda by d types.
Or
Huh?
Rayleigh criterion, right? Wait,
No,
am I?
that is no. In when we didn't do Rayleigh criterion. Come on, where did we cover Rayleigh criterion? In our some other thing we saw very similar relation, na? Ki some theta, some diverging angle is given by something very close to this, where something was different. This d was not d, something else was there.
Sir, Gaussian beam ka this thing.
Exactly. Gaussian beam, the waste at a point at a distance z, that is exactly given by the omega 0. That is the incident. I mean, it is essentially given exactly in the same way. If you just refer to the notes, previously ऐसा किया था ना, ऐसा type का जब waste जाता है, then this with they horrible. Right, and then we did this यहाँ पे, we did this ratio, right? That exactly comes up, that theta angle that you get of the spread of the Gaussian beam. If you take that this is some kind of a theta, ये type का, this is the thing. You take
Sir,
this theta,
but what is the relation of that
इसका
with this?
tangent करके, that exactly comes to something very very similar to this. So basically that tells you that the divergence of a Gaussian beam follows very much that of diffraction of a plane wave through circular aperture. It is very similar to that. How the beam after the plane wave spreads, it is spreads out through a circular aperture. It is exactly how the waist of a Gaussian beam evolves after it is focused, or the beam size. The tan theta, the theta that is, which is basically telling you how the, so this is your W0, na? This is your W0, and this is your basically this is W, right? And I'll exactly give you the thing that we measure. So basically we got that theta as lambda by pi W0, something like that. This is basically, this d is the input, right? Exactly what you, so this theta that you get here, 1.22 lambda by d, that is exactly what you finally have here, same way. Okay, so basically what the bottom line is that at this d, by the way, is this diameter, 2a is d, na? This is my thing, right? So this is telling you how this is expanding to this. Is that clear? This is my a, right? This is my theta. Oh, this has become horrible. Let me up this and do it properly. So basically you are coming in with this distance is d, you have this there, then this is basically what you get. Okay, this is your r0, this whole thing is z from here to here, and this is was the aperture. So basically the plane wave that was confined here, after it goes a distance z, the angle that it subtends with this, if I say that this is my angle theta, theta goes as some constant lambda by this aperture. And here if you see, if I want to find out how this theta, that is how the waist sort of expands, or the beam size expands from a focus or whatever w0, and that also is given by the lambda by pi. This is what you have here as w0, here you have as d. So the expansion of the waist is very similar to how a plane wave, the angular size of a plane, of the diffracted pattern of a plane wave through a circular aperture. So that also tells you guys, this is also interesting, that this here is actually like a plane wave. At the waist, what you have is nothing but a plane wave. This is another sort of an analogy which tells you that at the waist of the Gaussian behaves exactly like a plane wave, because the way a plane wave diffracts through a circular aperture is exactly how a Gaussian evolves as it goes away from the waist. I think this is very beautiful, right? Okay, so tell me, any questions? And then, okay, so officially this is the end of the course. Though I will want to take a class tomorrow to talk about optical tweezers. So that I hope is not a problem for you, where we actually, discuss what we finally have been, the model that we have been following all the time till now, which is how to trap a my nanoparticle. Now the problem, however, is that I think Bishwajit, one group is talking about optical tweezers, right?
Yes, sir.
So I cannot. It's not
Anisha,
fair
Anisha.
that uh, yeah, Anisha's group is talking about optical tweezers. So it's not fair that I make that task easy. So I will just talk about the basic stuff. So there are two types of forces. There is the gradient force and the scattering force. The gradient force is the one that is sort of stabilizing, and the scattering force is one that takes the particle away from the track. So those two things I will just maybe convert, John. So do you want to do the class tomorrow or sometime else? I mean, up to you. If you want, I can even, my syllabus is done. This is exactly what we covered last year.
Yes, sir. Exactly. You completed everything.
Exactly this is exactly where we ended last year. Last year we did not do optical tweezers because last year there was the exam straight. And there was no question of presentations and all.
Report कब
Sir,
submit करने से?
tomorrow we have exam actually.
So
Yeah,
So
bolo,
actually,
when?
we have an exam from 6 o'clock.
no, sir, the timing will clash.
No, I can take it. So bolo to फिर क्या होगा फिर?
So I suggest Saturday.
Okay, Saturday is fine. 5 o'clock.
Time
और
anytime.
early भी कर सकते हैं. हाँ? 4 o'clock.
I don't know. Depends on others. Anytime is fine.
Bolo, tell me. Saturday 5 o'clock or 4 o'clock?
Four is fine, sir.
4. Okay, Saturday 4 o'clock. That is just telling you about how tweezers, basic thing about tweezers. I think it is very, very simple, but yeah. After that, it becomes much more interesting. But did you guys really get the feel of diffraction from here? How construction happens? I mean, this whole bending of light around an obstacle. I think the way he constructs. I mean, Fresnel constructed these zone plates, which basically then are, that intersection of the zone plate with the Fresnel zones, I should not say zone plate, sorry, zones. That is essentially what the obstacle is for diffraction, and
This
it
should
really
work
tells
for
you.
generally any wave, right? Like it should work for
It
sound
should
also.
work. Yeah, absolutely. Absolutely. As long as you have a kind of a wave that is like, this spherical kind of thing, it should, of course, work. Like that geometry, you have to probably define properly somehow. But this is so nice, no? I mean, I don't know
Sound
why
wave,
these are not taught
why
later.
that is completely different type of wave.
It's longitudinal wave, but then if
Yes,
you think that the
But
disturbance,
anywhere in the current derivation, we didn't see if it's a longitudinal or transverse wave.
we
no,
didn't, that is correct.
when we wrote the equation, we started with the spherical wave, right?
No, I think what Anirudh means is this. Obviously, the input field and all that will probably not be the same,
Sir, will this
but
sound wave will become spherical in nature when it will encounter any aperture?
it should. No, I mean, if you have a point source, if you have a small microphone, small source of sound, that should point. Any point will go like a thing like that, right? It will just so drop. I mean, pond में सोचो ना. When in a pond, when you drop a stone, it is a spherical wave, right?
Yes, that is transverse wave.
But that's
That's
a
the whole
transverse
point.
wave. That's also true. Yes, that's a transverse wave, right?
Yeah, but it
Uh,
will be spherical only, no? If it's a very tiny source.
if it's tiny source, I think everything will be. Finally, disturbances also will. No, see what we see in the water stage. That is essentially just the envelope of the disturbances, na. The disturbances
Yes,
are also propagating like a sphere only, na. In a sphere itself, it's propagating. So sound is that you don't take the envelope; you take only the disturbances. I mean, directly the disturbance. Here you take the on envelope here. But then if you take the how the disturbance propagates, that's an interesting question actually. I have not. I think it is. Yeah, I don't see why it should not be.
sir. When I think of sound, I think of pressure waves. So, like having a spherically
ना,
sort of
एक just
pressure
सोचो
waves
ना तुम
augmented wave.
suppose see if you have a
Huh?
loudspeaker
Waves can
and place it
also
on
go
the.
vertically outwards, right? What's
That's
the
what I'm saying. So
problem?
if you have a loudspeaker, it's a big cone that if you place in one direction, the sound goes mostly like a conical thing. It's not a straight line. It goes like that. Now the smaller you make this loudspeaker, if you really make a small thing, I think it will go in a circle only. No.
Sir, it can be spherical wave. We saw one example a few months ago in the
Hmm.
Beirut. The bomb blast was not a good thing, but if you see the
Ha,
shock waves, those
ha,
were the
ha, ha. It
best
went
example.
exactly like a spherical. Absolutely right. In fact, earthquake में तो वैसा ही जाता है. Earthquake में
Then
wherever you have the
spherical wave is
epicenter,
possible.
huh?
So, the question that spherical waves in sound waves is possible, but I think
No,
his
no. So that's
question
what
is
no. That is what Priyanuj, you think of earthquakes, no? Earthquakes are
yes,
like that, right? It is an epicenter and it just goes radially outwards, very
yes.
clearly.
Yeah.
Absolutely, earthquakes are perfect example. So
So
yes, I
like,
think.
basically, I think most experiments with sound and light will coincide except for when polarization is involved, I
Ha
think.
ha ha ha. That exactly right. Exactly right. I mean, it is basically the disturbance तुम कैसा ले रहे हो, right? One is you take the envelope and is propagating like that, and the other one is the whole thing you take, right? It is just the disturbance is a longitudinal one. You take the, but the otherwise is the same exactly. I
Like
agree.
even refraction and everything will work
It
for sound.
actually works like that, no? It actually works like that. The refraction, if in fact, interference also happens, right? If you put proper, you will
Yeah,
get
interference. Also,
absolutely interference.
I've done that experiment. It's very
Uh,
easy to do. Like if you have two mobile phones, you can download
ah,
tone generator app. Just put 400 hertz or 600 hertz on both the phones and keep them like
close.
meter
You,
apart or
you
something.
don't even require two phones, just two different browsers in same phone. That also works.
Ha ha ha. Two same. Yeah. No, but that I actually
I'm,
what you're
I'm
saying,
talking about
I
I'm talking about like
just
something like a double slit experiment kind of thing. So
No,
you
you're
oh
talking
wow.
about beats, I think.
Yeah. Beats is exactly what I
beats is
saw.
also one thing, but I'm also talking about double slit, so same frequency. Like you keep two phones aside independently emitting 400 hertz or whatever,
Hmm,
1000 hertz,
hmm,
600 hertz, and then you
hmm,
go like you walk 2 3 meters away from the sources and you walk laterally.
हाँ हाँ हाँ.
You see
Go
maximum.
laterally, you'll find interference like come zada you'll find.
Yes, yes.
That is fantastic.
I've
Yes,
done this in,
correct.
so I've seen it happen.
You did it now,
No,
lockdown mein,
done it
before
1 or 2 years ago.
1 or 2 years ago. It's a
Aniruddha,
nice thing.
are you
Uh,
sure you saw it?
Heard
saw
it,
it
man.
mane?
In
Heard
Yeah,
PG,
it.
I did it in your room
yeah,
only.
he said he saw it.
PG, I
Heard
did
it.
it in your room only.
There's
Saw
actually
is observed here.
there's actually a
Observed
video.
is anything. But you could have seen it also easily, right? You take a microphone, put the waveform, you'll see it. Plot the waveform, you'll exactly see it. Right? You take a microphone, connect it to a computer, and
Yes, so that also is possible. Sir,
just
not
see.
related to
Put
this.
it in any of those, Audacity or
This
those
is
some softwares.
regarding
You'll
the
exactly see that.
Viva. Is it going to be
Huh.
everything in the course that can be asked about? Because it's very, very big.
It
Like we have
should
not
be.
given a Viva on such a large topic ever in our entire life. It's the entire 6 months
And
course.
you should no. What you should know, piano, is the connectivity. See, we connected everything nicely, right? So I will not absolutely ask you details. No way. Okay, but I'm going to ask you concepts. So just the way we connected stuff, right? You think of the pattern, that picture we had of that trap, right? And
You
immediately went.
mean the connectivity with the apparatus or just in
No,
general?
in the sense that the connectivity, man, what is the property of when you go from dielectric media, you go to metals, from metals you basically think of Kramer's chronic, from Kramer's chronic you go to anisotropic media, birefringence, uniaxial, biaxial, all that I did. Then we went to Gaussian, right? I mean, sorry, that first that ray matrix. I mean, how light interacts with mat in the sense of optical elements. Then we went to Gaussian. Gaussian say we basically finished with diffraction, right? That continuous thing. So, uska that awareness has to be there, and the basic understanding of how a performance of a metal will change as you go into, I mean, sorry, how when you change a glass interface to a metallic interface, how everything will change. What is the chief takeaway? That is what the concept is, right? When you go say, my target has in this course has been that 2 years 3 years down the line, when you will not be doing, if you are not doing, of course if you are in this subject, then you will need to do all these things. But even if you are not doing this subject, that connections that we made in this course, that will kind of stay with you. I want to check if those connections have been made. I will certainly not ask you to derive things, like, no way. But if I ask you, what is this, how does this zone plate thing work, what was the construction, right? I mean, can you explain diffraction, the bending of light from the Fresnel-Huygens theory, right? So that you should be just able to simply explain that, okay, this is how it happens. Not no like complete derivations, but it goes like a series, and then you just block, you take odd terms, you'll get complete destruction, and if you take even terms, you get zero. If you take odd number of terms, you'll get almost the same value, which is a beautiful thing, right? I mean, since they are all close to each other, so it's like really you get that kind of a pattern that way, and yeah, it's really quite amazing. So things like this. So the overall understanding of the course, with not with with real sort of regard to detail. So it's going to be a tough thing for me as well. But I will test basically what concepts you have developed, not what, I mean, the knowledge thing in a Viva I never ever try to do. Okay. By the way, so I saw the routine, no? So that is basically, I think first, so second to eighth you have exams, right?
Yeah, the first week is like exams nearly every day for everyone.
So eighth, no. So then we leave it completely, no? So we can just from 8th to 20th we can finish everything, right?
So we have exam on 10th as well.
Yeah, like if you start from 10th, I guess
Okay,
every one
10th
of
karo.
us is very free after 10th.
और 10th से ही करो.
Yeah.
उसका एक ही problem है कि okay, by 21st I have to submit all grades.
So
Can we do some of them before? I mean, I think okay. So I think Bishwajit, you start working with these guys and fix up a routine. See, the Viva, obviously, all of them don't have to be, absolutely don't have to be there. Vivas, we can. So, for example, Hitesh's exam ends on 10th, right? But others are going to end even before.
No, sir, my exam won't end on 10th. I'll have another exam on 14th.
Arey baapre.
But
What exam
there
is
is
on
this,
14th?
but
It's
there
not
is
in the
this
routine,
gap.
no?
But there is this
Huh?
gap, 11th, 12th, and 13th. So that's why I
Okay.
said KVM.
Hey, but routine mein to they did not give till 14th, no?
Sir,
we
it's
have a
PH 4106.
quantum
Oh.
field theory.
Yes.
Arey baapre. Okay. But that is given in the routine.
We
Yes, sir.
haven't set the routine, but there's an exam.
Yes.
Hey, oh, but I don't. I'm almost sure that is not there in the routine. Yeah, 1 minute.
You
Let me
can
just
check
check
it
and tell you.
because our instructor told that we have an exam.
Hey, एक second. By the way, I told them that I am not taking that. Hold on 1 minute. Hey, that is remarkable. No, Shomitra sent that routine thing. It's a timetable. Oh, no. Hey. Okay. Mm-hmm. Correct.
I think
Oh, PH 4101
ऐड
is
हो
also
सकते हैं
there.
क्या नहीं?
PH 4106 is on 14th.
Yes,
Oh,
so the
baapre.
10th is exam for all physics majors. So if
Mm.
maybe it will be unfair if you just start the next day for the person who gets on 11th. Maybe from 12th you can start completely.
About 12th to 21st तो problem होगा ना.
No, because whoever gets on 11th will
Mm.
be very unlucky because it will be like one day to revise everything.
No, why Priyanuj, you are telling that you will give the your presentation in the last week or something, right? I mean
yes,
this week.
We are giving no, we are giving presentation on 15th. I think that was decided.
15 to 18.
15th. How can you give the presentation 15th? Means, presentation will be before, no? That's why I told you that the last week
Hey,
of
why don't
November.
we finish the Viva? I mean, early. हाँ, तो Viva can start, no?
Sir, it was decided
What
that
do you
the
think?
Viva will be from till 15th or something, and from 15
Hmm.
to 18 we'll have presentations.
Oh, okay. Oh,
Oh yeah,
okay.
so yeah,
15 to 18
I
because
think 12 will be very late.
I forgot.
So I
Okay.
thought we were doing something like that. That according to those who don't have a particular exam on that day, will take care of
That is
that.
exactly. That is what I thought I would do the Viva. So Viva, why don't you guys just has this timetable been sent? Not really sent, no?
Not to students.
Not to students. Okay, I got. So so let me
Sir,
see. So fourth
I was
year I'm seeing. So physics has third, fourth, fifth,
Sir, there is no point in looking
seventh.
at the timetable because we might not have a particular course. So what I suggest is
Hmm.
we can collect a dates from the students of this course
Yes,
who do not have exams on what dates, and then
yes.
use that to
So
create it.
do that quickly. Finally, I think, right?
Okay.
Because I would suggest that you finish that before the 30th or something. No,
No,
before the. I think
Mohan,
today is
will you
Thursday,
ask
right? So
what free days we have or what days do we want?
Free days when we don't have exams, we submit that to sir, and he creates a random.
that is perfect. When you don't have exams, that is perfect. But yeah. Who does not have exam on which day? So that way we will schedule the Viva.
Yeah,
Okay.
so we'll have to look into that.
Yes. We will schedule the Viva that way, and the presentations then we'll do just what? When did you say 15th? No.
Yes, 15th to 18th or 19th, whatever.
15th to 19th we can finish, or 18th also we can finish. Start then 15, 16, 17, 18, 19. 5 per day. Fine, absolutely fine.
Yes.
Sir,
That
we
is
have
fine then. That
another
is decided then.
presentation
ठीक है?
for research methodology from 15th onwards. So it would be better if you can tell us the rough slots so that we can convey this to Bhavta sir because
तो तुम तो
there would
so
be clash.
exactly no so वो ही करो ना. So suppose we are basically having so 15 to 18 that is fixed.
Yeah, dates are fine, but for
Okay,
particular
so
group,
15th to
it should
18th
not
if we do
clash.
it, yeah, so 15 to 18 तुम उसका हफ्तों का मॉर्निंग में कर डालो, and hours we can do from say 3 to 6 or something.
Okay.
Okay, so 3 to 6 we do hours. So 15, 16, 17, 18. So Bishojit, there are 19 groups or how many groups? 19 groups, I think.
19 groups. Yes.
19 groups, right? So 4 days mane 5 each. So 5 each mane 2.5 hours. Okay, so 2.5 hours mane roughly we keep 3 hours. So then yeah, 3 to 6. 15 to 18, 3 to 6.
Okay. 15 to 18, 3 to 6. Okay.
Oh, Viva ka thoda you just so Rohan and whoever, I mean, yeah, all of you just send us the dates, and maybe Jibon and Vishwajit, if you guys we can sit together and just decide when we keep for whom, and just share it with them.
Yes.
Okay. So if you guys want, then maybe tomorrow after the exam you can also sit with Vishwajit and decide.
So I'll create a Google Chrome and
हाँ,
my
Google form का exactly Google form डाल दो, डाल के let us see from there. Okay, so that is decided then. 15th to 18th presentation from 3 to 6, and other one from this thing. And report you have to give me. Actually, it is better you give me before the, or maybe by 28th to give the report. Sure, I must, because 21st is grade.
Sir, but like we don't know the exact exam dates. We haven't received any timetable from the academic office.
Do you want me to forward this?
So even if you forward it, it is possible that
It may
some
change.
instructor might change it.
Hmm.
No,
When?
no, but we
No,
are
but
sure
when
that
will they
after
forward?
10th
No.
we won't have, right? The 10th one.
We are not sure of anything as of they don't send any timetable.
Oh, but 14, 15 तो बोला ना, इसका तो होगा.
So
हितेश का है.
all these, nahin, that is exam of every one of us. But the point is, the instructor told us 14th as quantum
Oh,
field
अभी
theory.
और एक mail आया. Hey, I think there is one more mail.
So all
Oh,
these
अभी
dates that we know are only through the instructors as you
Oh,
receive
this
the
is
timetable.
spring timetable. Look, this is spring timetable. Sorry. This is different. Okay, this is different.
Just to be confirmed, is
Hmm.
the quantum field theory report and Viva, the presentations are done before 15th? We are supposed to do this.
Yes, I think so.
Okay, so 15 is the deadline for QFT. I mean PH 4106.
Yes.
Okay, thanks.
Okay, so then ours is fixed. The presentations are fixed then. 15, 16, 17, 18.
Yes, sir. But
And the other
regarding
one, Viva, you have to decide. Tell me.
Viva, that will be decided
I
once we
don't have a
receive the
problem. I mean,
timetable and semester
every
timetable.
day I can take 2, 3. Okay. But timetable, I'm sure you're not going to receive on 30th, right? First is the exam. I'm sure you will receive it maximum tomorrow, I guess.
Yes, yes.
I'm
So
sure.
I'm just
It
waiting for
cannot,
that.
does not make sense. Yeah, I'm sure you're going to reach. So anyway, so try to finish by 30th, decide the Viva date.
Okay, sir.
ठीक है? Okay, फिर चलो. Let me stop. Hopefully it will come to thankfully. Okay, good.